So if you've looked at all at the sheer length or complexity of this PowerPoint, you'll see that it's one of the heavier ones. There are quite a few questions in exam 2 that will be taken from this PowerPoint, and I've marked them in the slide. One of the things that's important is just to start off by understanding what we mean by association and measures of association. So association is the relationship between a risk factor and an outcome. For instance, I just opened up a browser and found out that Newsweek is reporting that there may be a relationship between the number of people who are hospitalized for COVID-19 and obesity. So the question is that a true relationship, or could it just be an error found in the data that's been collected so far? So measures of association are important because they help us to sort out what is the truth or the integrity of the study, or what could be understood by some kind of error in the methods or the design of the study or how the data was analyzed. Slide follows closely after our introduction. It introduces the concept of bias, which is defined as any systematic error in the design, conduction, or analysis of a study. This focuses on how important it is to pay attention during the design and implementation phases of a research study. Because if you don't catch the errors, the systematic errors, until the analysis of the data, it's going to be very hard to fix it at that point. You could evaluate it, but you can't fix it. So we've got a definition of bias. We understand now that it's not just a single error where somebody messed up, and it has nothing to do with whether the investigators had some kind of a prejudice as they went into the study. So as we mentioned in the last slide, a bias has been found when there's an error reporting some kind of a difference between the variable or the risk factor and the outcome that we found. And it's not a true relationship, it's not a true association, there's a bias. So we can have a bias away from the null hypothesis or one toward the null hypothesis. Remember that the null hypothesis is when the researchers either directly or indirectly state that there is going to be no relationship between the variables and the outcome, that it won't make any difference in the variables being studied. So a direction or a bias away from the null means that they found too much significance that is really not true. The association was exaggerated. And a bias toward the null means that there really was a stronger relationship between the independent variable and the dependent variable, or the outcome that they found, that there really was one, but the researchers failed to find it. So that would be a bias towards the null. For example, we're going to be talking about relative risk later in this PowerPoint, starting in slide 7. But let's say that the true relative risk, so that the true relationship should have been the number 2.5. A small amount of a bias towards the null could be if that's reported as 2.3. A large amount of bias towards the null could be if the relationship is reported at only being 1.0. And it can go the other way. We could over exaggerate and get 2.8 or 5.0. So bias can arise in all kinds of study findings. It is important, again, in the analysis phase, bias can only be evaluated at that point, but not fixed. So that's why it's so important that the study is carefully checked before the study is implemented. So at this point, the study has been completed. All of the data has been collected and analyzed, and the researchers are ready to draw conclusions. A mistake that they could make at this point is to assume that because of the data that they infer causation when they should have just stated that we have observed a relationship or an association. There's a huge difference between assuming causation or stating an associative relationship. It's very important that researchers not get that wrong. To actually infer causation from the data means that very rigid protocols in the design and implementation of that study and repeated studies have been done so that they have ruled out any impact from another variable that could possibly have interfered with the relationship they found. When there's just no question in mind, then and only then can the researcher say that this causes this. And for an example that it took many years, but they finally determined that they could draw a causal relationship between smoking and the risk of lung cancer. But it wasn't done prematurely. Again, very rigid research was done before they could make that claim. Generally, what's stated at the end of a relationship is that there is a strong association or a moderate association between these independent variables and this dependent variable or outcome. A useful chart, but we are really looking only at the middle column. So the title of this PowerPoint was Measures of Association. We've talked about association, but what we mean by measures are what are the tools that are used to determine how closely aligned this relationship or this association is. We've got two tools listed in that middle column. One is relative risk, which we're going to find out is the main tool or the main measure that's used in cohort studies. And the other is odds ratio, which is the principal measure used for association when we are doing case control or cross sectional studies. The reason is because a relative risk requires that you have incidence data, and that's not possible in a case control or a cross sectional study. On the top of this slide, it reviews both of those measures of risk, relative risk and odds ratio. Both of them, what they do is allow us to compare risks. But there is another type of risk that's added on the bottom of the slide, which we will start looking at in PowerPoint slides 21 and 22. And that is an attributable risk. That has a different purpose. Attributable risk is valuable to determine the effect or the impact related to that risk factor. So again, the first two compare risks, and the second one determines the impact related to that risk factor on the situation. This slide is talking about how to calculate relative risk, which is actually quite simple. You know how to calculate an incidence report, and you know how to find out where it is reported. And it's the incidence rate in those who have been exposed to the risk factor you're studying, divided by the incidence rate who did not have exposure or in the risk factor that you're studying. So in the notes section, for instance, what I looked at is colorectal cancer, and the exposed was those who had taken hormone replacement therapy, and the unexposed were women who had not ever been on hormone replacement therapy. And when one was divided by the other, the answer was 1.4. So again, in learning how to interpret that, we want to be careful to not make it a causal statement that you would say something like, you know, you have 1.4 times the chance of developing colorectal cancer. It's really important that we speak and use our language carefully when we interpret study results. So it would be much better to state that the relationship between hormone replacement therapy and colorectal cancer was 1.4 times stronger compared to the relationship of 1.0. that was presumed for those who had never taken hormone replacement therapy and developed colorectal cancer. This table is another way to develop the incidence rate in the exposed and divide it by the incidence rate in the unexposed. You can create what we call a 4x4 table. You can see the columns there is the status of the disease. They have the disease versus they don't ever get the disease. And the rows are those who are exposed to the particular risk factor and those who are never exposed, just as we simply discussed before with colorectal cancer and taking hormone replacement therapy. Each of those cells is given a letter name, A, B, C, D, going across from left to right and then from top to bottom. And that'll be important in the next slide because we can simplify this down to a formula. Slide looks more complicated. It's actually quite simple. And I'll prove that if you can take the numbers from PowerPoint slide 8 and create your own 4x4 table, you will see that A divided by AB plus B divided by C plus D indeed comes up with the particular relative risk that we were looking for. So this is the third slide, and it actually follows through by giving you the answers to the computation that we started in slide 8, so that you'll know if you're doing it correctly. When you follow it through and you're done, your answer, the relative risk is equal to 5. And in this case, the disease was bladder cancer that we used as for an example, and the risk was smoking versus non-smoking. So it's important, again, to follow through and make sure that we interpret this by stating the conclusion or the summary in the precise words that are correct. So the interpretation of a relative risk of 5.0 in this particular disease and risk factor is that the probability of bladder cancer is 5 times as great in smokers as in non-smokers. Or another way you could say it is avoid smoking, since it is associated with 5 times the risk of bladder cancer. So when you're the primary care provider and you're reading research studies, it's just so important that you interpret the results and share that information correctly with your patients. So for the exam, you'll need to know how to calculate relative risk, but you'll also need to know how to evaluate it. Again, when you're the primary care provider and you're caring for patients and you're reading research studies and you go to the conclusions at the end and it reports things such as relative risk, how do you determine the correct interpretation of that study? Generally, there's an easy rule, and that's if the relative risk is equal to 1, the exposure is not associated with the disease. If it's greater than 1, there is some association with an increased risk of disease. If it's less than 1, the exposure actually is related to a decreased risk of disease. So in other words, that risk factor, let's say it is exercise, may be protective against the development of the disease that you were studying, which was congestive heart failure. So we look for that greater than, equal to, or lesser than sign when we interpret the relative risk of a study. Moving now from relative risk to odds ratios, which are used in case control and cross-sectional studies. Remember, I think what a cross-sectional study is pretty clear, but remember how we set up a case control study. At the very beginning, we determine what the outcome is that we want to study, such as congestive heart failure or spontaneous abortion. And then we look back in the data and we look at who is exposed to certain things earlier in their history and compare, and we call them the cases, and then we compare them with those who are never exposed to that risk factor previous to when they came down with this negative health condition. Because of that, we've already grouped those that we're interested in studying, so we will have no new cases. And if we have no new cases, we have no incidence data. And if we don't have incidence data, then according to the way that we set up relative risk, we cannot calculate a relative risk. So how do we measure association in those two types of studies? We use instead an odds ratio. So in setting up an odds ratio in the top bullet point, what you do is you compare the odds that the cases were exposed to risk factor divided by the odds that the controls were exposed to that risk factor, and then divide it out. And interpreted, it is interpreted the same as a relative risk. In other words, equal to 1, greater than 1, or lesser than 1, which you can read on that slide. This should look familiar. Again, it is a 4x4 table. This particular one doesn't have the totals put in because it wasn't important. But we set it up again with the disease status on the columns. Those with the disease are in the first column. Those without the disease are the controls in the second column. Similarly, we have the exposure in the rows. Those who have been exposed in the top line, those who have not been exposed in the bottom row. And note, by the way, that the positives are always in the upper left. So every time you create a 4x4 table, the upper left will be those with the exposure to the risk factor and those with the disease. So, because if you get that wrong, then you won't set up your 4x4 table right. So we again have A, B, C, D. And what we do this time is we cross multiply. We multiply A divided by A plus C and divide it by C over A. Well, you can see it there. You don't need me. But if you do it that way, if you remember from your algebra that when there's a common factor there, A plus C or B plus D, that those cancel out. So A plus C cancels out both in the numerator and the denominator in the odds that a case was exposed. And B plus D cancels out in the odds that the control was exposed. And we end up with a much simpler A divided by C and B divided by D. But then we can go another step further, and we can take A divided by C, which again were the odds that the case was exposed, divided by the odds that a control was exposed, B divided by D. And when we do the math, when you divide by the lower one, you of course flip it so that the denominator becomes the numerator, if you remember your algebra. And at this point, we get our simplest form, which is AD divided by BC. And that's what you need to remember to be able to calculate. So again, if you do your 4x4 table after that very long explanation, all you've done really is cross multiplied. AD must go first, that's in your numerator, and BC must go in your denominator. So starting with the cases that have been exposed, cross multiply across the diagonal and divide by the other diagonal. And you will have the way that you calculate an odds ratio. So that last slide, I went at length to explain how the math calculated out in a case control study. In this slide, we're going to actually use some numbers, and we're doing it in a cross-sectional study since both of them use an odds ratio. So these are the numbers that we found and placed into our 4x4 table. Disease status, HIV positive, first column, HIV negative, second column. Exposure to IV drug user is in the top row, and not users of illicit IV drugs is in the second row. So if we follow the AD divided by BC, as we determined in the last slide, then we get 61 times 312, which ends up, by the way, being 19,032 for the numerator. And then if you multiply 27 by 75, you get 2,025. You can do the math, by the way, with your own calculator. So cross multiplying both of those. And then if you divide the numerator by the denominator, the odds ratio is 9.4. So again, if we're going to interpret that, that's certainly much greater than 1. So there would be a very, very strong relationship between the risk factor of being an intravenous drug user and HIV status. This slide just works out the number, and the interpretation again is careful. The red, and that's the odds that an HIV positive person uses IV drugs is 9.4 times the odds that an HIV negative person uses IV drugs. What again we are avoiding is making any stronger statement that would suggest that there's a causative relationship between drug use and HIV status. So I want to remember what we're doing this all about. Both odds ratio and risk ratio are used to determine the amount of bias and make sure that the results of the study are valid. So an odds ratio is a good approximation of the true risk or the true association between the independent variable, which is the risk factor, and the dependent variable, which is the outcome of interest. So the true relationship of that risk factor is correct if 3 conditions are met. First of all, if the controls are representative of a target population, and the cases are representative of all cases with this condition. So for instance, if the controls were different in a rural area of Alabama versus New York City, which is where we wanted to apply the study results to, then that wouldn't fit because they're too different. Maybe they report them differently. And what about the cases? What if we looked at the cases of women with HIV who are between the ages of 18 and 25, but we want to apply this to a nationwide situation in which, as we know, girls as young as 15 or women as into their 60s could certainly acquire HIV, and there could be a true relationship there. So the cases and the controls need to represent the population that the study is meant to be targeting. The third condition here is that the frequency of the disease in the population is small. If there's a really high prevalence rate of this disease in the population, then what happens is the odds ratio exaggerates that risk, and it's not a true indicator of the association between those two things. This table is just a summary of what we talked about before. When you're looking at measures of association, which type of studies would you use a relative risk, and which studies would you use an odds ratio? And you should know the difference for exam 2. The last row there introduces a different type of study design, and that's an ecological study, which is an observational study, not with any individual data, but with data collected at the whole population level. And in that kind of a study, actually you cannot use either a relative risk or an odds ratio to determine association. So we're going to introduce something new in this slide, and unfortunately, confidence intervals are not in the Gordis textbook. So you're just going to have to listen carefully and maybe a couple of times to my explanation until you get it. Ideally, we would like to collect data on every single person in the target population so that we would have complete data. But you and I both know that that's rarely possible. That generally we draw a sample of participants, and then based on our analysis of the data from that sample, we assume that if we've done the study correctly and all conditions have been met, that we can draw accurate conclusions about the target population. But we're never 100% accurate. So what we do is we come up with an interval, and we say that if the result that we got on our sample was, for instance, 5.2, that in a total population, 95% of the time we can be confident that the true number would have been between 3.2 and 7.2. Or another way of saying is, if you did this example, this study 100 times, the sample result that you got, the 5.2, would have fallen between 3.2 and 7.2, 95 out of those 100 times you did the study. Or I'm going to try one more time of interpreting it as, based on sample statistics, an odds ratio of 5.2 with a confidence interval of 3.2 to 7.2 suggests that there's a 95% probability that the true odds ratio in the population would be likely to lie in the range of 3.2 to 7.2, assuming there was no bias or confounding. Slide repeats what I just said about interpreting a 95% confidence interval. Notice that the two confidences that are usually used are 95% or 99%. So if the particular thing that you're studying needs to be very, very precise, the researchers might set it up instead for a 99% confidence interval, which means that 99 out of 100 times what you found in your sample study would have been found in the full population 99 out of 100 times. And we can apply that again towards either an odds ratio or a relative risk. When you're comparing confidence intervals, and I know you're going to see them from now on as you read your research studies, you'll look for those square brackets and the notation of CI, and you're like, okay, what does this mean? If you see a really large confidence interval, that doesn't give you the same confidence that you can apply this as if you see a narrower confidence interval. So in my previous example, if the odds ratio had been 5.2, but the confidence interval for 95% was somewhere between 0.8 and 19.8, you'd say, well, 95 out of 100 times it's between 0 and 20. I don't really know how to use the value. But instead, if that confidence interval is between, as we said, for instance, 3.2 and 5.2, now that gives you something to work with. Practice what I said. If you saw these three reported confidence intervals, which one would you be more likely to infer causation or to state that there was a good and strong relationship with? Which of these three? I said that we would be looking at a third type of determining risk in this PowerPoint, and this is attributable risk, which we will discuss on this PowerPoint slide and the next. This is discussed in Gordis, so you can read those pages 230 to 237. They're also important because on page 231, it talks about why this is used. Why is it determining attributable risk important? So first of all, we're just going to start with a definition that I gave you before, and I'll repeat here. Attributable risk is defined as the incidence rate in the exposed minus the incidence rate in the non-exposed. So you can see with the underlying thing that in this case, we're going to be doing subtraction, right? 6 minus 4, or the difference between 6 and 4 is 6 take away 4, and we get 2. So we're going to be looking for that subtraction sign as we calculate this. And again, the bottom of this slide lists 2 of the values of using attributable risk. It's used to determine the amount of disease incidence that can be attributed to an exposure from a specific factor. And then that might help us to develop disease prevention approaches in order to reduce that exposure. So this slide gives us the formula for how we will determine attributable risk. Notice that the letters A, B, C, D refer to setting up a 4x4 table just as you did before. So you can go back to PowerPoint slide 10 or 8 and 10, and you can put in the exact numbers yourself. A divided by A plus B, subtract C divided by C plus D. Again, it's a measure of risk difference, so you can tell that you're going to subtract. When you do that, you'll get 50 divided by 400, subtract 15 divided by 600, which if you reduce that becomes 0.125, subtract 0.025, and the difference is 0.1. So I wanted to give you those answers so that you could be confident that you've calculated it correctly. So if you get 0.125, subtract 0.025, and the difference is 0.1, you have set up the table correctly. So again, in how would we interpret this? We would say that in the disease of bladder cancer, 1/10 of the risk of developing bladder cancer can be attributed to smoking status. This is probably it's the last 5 slides in this PowerPoint, but it might be some of the most confusing ones. So I'm really going to do my best to explain it, but also make sure that you read carefully in your Gordis textbook. I want to introduce first something that you're probably the most familiar with, and that's the P level. You're used to looking at research studies and examining a P value, and you usually see it as 0.05 or 0.01. The question is, what does that mean? The p-value or the probability level is defined as the measure of the likelihood of rejecting a false hypothesis. Again, this entire PowerPoint has been all about making sure that we reject false claims that could have been there because bias was introduced in the design of the implementation or the analysis of the data. We want to reject the likelihood that researchers would make a false claim, would say that this is related to this, and it really isn't. That's a false claim. So to what degree would we allow a risk that a false claim was made? If we set the P level at 0.05, then we are going to allow that there is a 5 out of 100 chance that these researchers could have made a claim at the end of the study that they shouldn't have made, that it was a false claim. If we say that's not good enough to me, this statistical study is too important to risk making a false claim. So instead, I will set the P level at 0.01. That means that out of 100 times, 99 times, the right claim will be made, and less than one time would a false hypothesis be made. Now, one of the ways that we can increase what we're going to call the power level, or the chance of rejecting a false claim, is by having an adequate sample size. So our third bullet point there says that typically the power level increases as the sample size increases. So if you're doing a small pilot study, maybe you just want to see how feasible it would be to do a larger study at a later time. You want to be really careful when you're doing that, because the sample size for your pilot study is probably going to be very small. And so it's far more likely that you would make a false claim. And therefore it has to be read and interpreted very carefully. To start by reviewing something that I'm sure you've seen before, and so this will not seem that difficult to you. This is called a normal distribution curve. So notice that if you were to fold the paper right down the center of this data, that it would be equal on the right and the left. It'd be an exact match. And what we've said before is, just in case the data would fall perfectly into a normal curve, and it usually doesn't. So normally what happens is that statistically, they adjust the true data until it can resemble in some fashion a normal curve. And that's way beyond my brain power to figure out. But once they get it to that, then there are certain rules. So for instance, they can determine how much data is within one standard deviation above and below the mean. And so we call that, if you add the numbers there, 19.5% of the data is a half of a standard deviation above and below. 15% of the data is another half of a standard deviation above and below. So if you add all of that, then 68% of the data is within one standard deviation above and below the mean. We do the same thing when we go beyond that. We add the next half standard deviation, we get 9.2, and the second half of that standard deviation, we get 4.4. That means that now if we can go between 1 and 2 standard deviations, we're going to add another 27.2% above and below, or we now have a combined total of 95.2% of the data that is within 2 standard deviations of the mean. Let's do it a final time. Let's go another half of a standard deviation, that's 1.7. And the final half standard deviation is 0.5. If we add all of those, both above and below, we get an additional 4.4% of the data. And if we look at all the data that's within 3 standard deviations of the mean, we get 99.6% of the data. Those are very famous rules. We call that the rule of 68, 95, and 99.6. That way we will always know that 99.6% of the data is within 3 standard deviations. 68% of the data will always be within 1. Why do we care? What this means is that none of that data within 3 standard deviations is worth anything to us as researchers in terms of making a claim that we have significant findings. It's like you could put a big X through all of the data, and all we're looking at is the percent of data that falls outside of 3 standard deviations, because that's the only data that we could say, you know what, this just wouldn't have happened by chance. This data that is above 3 and below -3 standard deviations, This is significant data. It could not have happened by chance. Because of this data, I can now make a claim that my research findings are significant. So what we do is the researcher sets what they're calling an alpha level to determine how much risk that they are willing to take, that, and we're going to call this how much risk of a type 1 error, which I will introduce on the next slide. So they set the alpha level and then they compare that with the probability level that I discussed in the previous slide. So we've got an alpha level determining how much risk of making a what we're going to call a type 1 error. And we have a probability risk level that determines what is the chance that this could have happened, this could have happened by chance, and therefore there could have been a false hypothesis, and we compare those two numbers. So first of all, what is the alpha level? It is known as the level of significance. The number alpha is the threshold value that we measure the p-value against. So I said we were going to compare alpha levels and p-values. It tells us how extreme observed results must be in order to reject the null hypothesis that said it didn't make any difference. There wasn't any significant findings at all. In order to reject that and make a claim that there were significant findings, we need to compare the p-value against the alpha value. And if we do it incorrectly, then we could make a false claim. And that would be a spurious claim that the results were significant when in truth they really weren't. So now we are going back and reviewing what the p-value was. We're going to call that the probability level of a test statistic. It tells us what the probability is that that test statistic, in other words, that data point, could have occurred by chance. In other words, how extreme was that data point? Because if it's not extreme enough, if it's within the major 3 standard deviations, then it could have occurred by chance. It can only be significant if it's lying on the extreme tails. So I said that we would compare p-values with alpha values. So what we do is if the p-value is greater than the alpha value, then the result is not statistically significant and it could have occurred just by chance. In saying that, what we do is we reject the research hypothesis that we found something important, and we keep the null hypothesis that says there was no significant difference. On the other hand, if the p-value is less than the alpha value, then we say that that particular value, again, it's sitting way out of the tails of the data points, that that's significant. And the null hypothesis should be rejected, and the research hypothesis will then be supported. And at that point, and that point only, can the researchers make a valid claim that what they found of the relationship between the risk factor and the outcome is significantly associated. So we're going to introduce one more thing in this final PowerPoint slide, and that is a type 1 error. There are type 1 errors and type 2 errors. Type 1 errors are related to the alpha level. Type 2 errors are called beta. So we're just going to look at type 1 error at this point. A type 1 error means that the researchers rejected the null hypothesis that said that there's no difference. They rejected it and they made a claim They should have accepted it because in truth, there wasn't a significant relationship, so they made a false claim. Whenever you make a false claim of an association that truly does not exist, that is called a type 1 error, and it's considered very serious in health science research, particularly because, of course, we're dealing with real patients and real diseases. So if the alpha level is set at 0.05, we see that that means that 5 out of 100 times a type 1 error is made. If we can't accept that, because what we're studying is very, very sensitive, then it's better to set the alpha level at 0.01. That would mean that only 1 time in 100 is it likely that a type 1 error is made. And the way we are going to remember type 1, and then later we'll add type 2, is by the bold letters RA. So if you see below, the first R stands for rejected and the bold A stands for accepted. So this is what will help you remember it for the exam. A type 1 error means that you rejected the null hypothesis when it should have been accepted. We're going to find out that a type 2 error means that you accepted the null hypothesis when it should have been rejected. So type 1 is RA. Just remember RA, and it has everything to do with how you respond to the null hypothesis. So read that over a couple of times and you should have it for the exam.